Hi everyone, my name is Elston and together with my partner Niaz form the team Black Gold. Our project revolves around using satellite imagery to predict volume and ultimately oil stock price for casual investors. The best way to predict volume is by analyzing satellite imagery of oil tanks. Oil storage tanks play an important role in the global economy. Crude oil is stored in tanks at many points between extraction and sale. Storage tanks are also used by nations to stockpile their oil reserves. The volume of oil in storage is an important economic indicator. It indicates which oil producing nations are increasing or decreasing production and gives a window into the global demand for energy. At the same time, oil storage information is not transparent. Nations may hide information about oil production, consumption, and storage for economic or military reasons. For this reason, companies like Planet and Orbital Insight have made a business of collecting satellite imagery of oil storage tanks and estimating reserve volumes. So here's our homepage of our website. On this page, we briefly explain what Black Gold is all about and what we do. So if you have time, you can take a look at it. It's a few different sections. So now moving on to the sign up and login system. We decided to go with Firebase due to it being easy to understand and straightforward to implement. Initially, I still struggled a lot to create a functional system since I didn't quite understand how Firebase worked and how to integrate it properly into our website. After much struggle, I finally managed to get it to work. So essentially, it works just like any other sign up and login system. So let's say I want to make an account. So test@gmail.com and a password, create account. It says successful, and then we press OK. It'll bring you to the dashboard page. Now, just to test in the login, press login and type the same credentials in again. So if it's successful, it'll bring us to the login page again. So, the dashboard page. So this dashboard page is where our main app will be hosted. So right now you can see there's this graph from TradingView right here. So it's just like a normal trading graph that you see on other trading websites, which allow users to monitor the price of a stock, or in our case, light crude oil futures. Users are able to manipulate the graph. I zoom out and see the past price. Then they can see different pieces of data on this graph relating to specifically light crude oil futures. So if users scroll down, they can see three checkboxes here and apply changes button. So upon clicking certain checkboxes and pressing apply, users will be able to see an extrapolated line of this graph here, which we're currently working on integrating. My partner Niaz will tell you more about this later on. So essentially what happens is that based on which checkbox users tick, our machine learning algorithm will scan current satellite imagery and use that data to determine if the future oil price will increase or decrease, then display it as an extrapolated line on the graph. So now that you have a rough idea about what our algorithm does, Niaz will explain the finer details of how the program operates.
Hi, I'm Nias from Black Gold. As Elston has explained, we have made use of machine learning to output results that we need, which I will explain in further detail. Crude oil, and by extension oil tanks, may not be the most exciting topic to most, but I hope to change your mind with our approach to it. Now, to make our project work, we have employed the use of image recognition. The basic idea behind our project is to recognize oil tanks from satellite images, estimate their leftover capacity from the shadows cast by the oil tanks, and compare the trend in oil supply. If the supply went up, price is expected to fall. If supply went down, price is expected to rise. Now, how do we plan to execute this? Through the use of machine learning, of course. Now, as you can see in this document, there's a picture of a man on a horse. Now, it's abundantly clear to us. It's almost instant for us to recognize what objects are in this image. However, what does a computer see? A computer simply sees rows and rows of pixels and pixel values, such as red, green, and blue. How is a computer supposed to recognize what objects are in this image? Now, of course, if exactly the same man was in the image that you wanted to look for, at the same angle, same lighting, the computer would be able to recognize this because the pixel values would be the same. But however, if you want to recognize a person in general, how would you go about doing that? Now, as you can see below, there's an example of milestone2 working its magic and registering what it thinks are objects in the scene. It may not have seen this person in the background before, but it is still able to recognize that as a person. And that is the power of machine learning. Now, such a technology is what we have employed in our own project. As you can see here, this is the raw data set for our images. These images are these images are from Google Earth and overlook various oil tanks from around the world, which we have used to train our machine learning model. Each image is fairly large, and we have subdivided 100 of these large images into 100 of their own, so we got a total of 10,000 sub-images. Each image is 512 pixels by 512 pixels, and this is what we feed into our machine learning model. Now, preparing this dataset was supposed to be a breeze. However, we encountered many roadblocks. The JSON file that is supposed to contain information about the images did not get initially recognized by our model, requiring us to debug for a very long time, asking questions on many forums before we finally solved the problem. Our dataset was 10,000 images long, and modifying the JSON file manually would have taken an extremely long time. So we wrote several Python scripts to modify our JSON file and allow our datasets to be recognized by our machine learning model. Now, eventually, when our model was trained, it could barely recognize any oil tanks. We did more research and came across the concept of transfer learning. Now, transfer learning is whereby you use a pre-trained model and train it on an unrelated data set. So, example, if you have a machine learning model that is completely untrained, the weights that have been applied in the model would be random. And given that our dataset is only 10,000 images strong, it will be difficult to get accurate results from simply training on such a small dataset. So what we did was, through transfer learning, we obtained a model from milestone2 that has already been trained on another image dataset. So it's been trained on a dataset of 100,000 images, and we simply used that pre-trained model and trained it in our own dataset to get more accurate results, considering we had a relatively small dataset. Now, this newly trained model was much more accurate, but still fell short of our expectations. Now, through the use of Google Colab, we were able to take advantage of their free GPU processing power and train our model for 9,000 or more iterations in a reasonable time frame. The resulting model is extremely accurate on our validation dataset, giving us an average precision of about 87%. As you can see here, it's a bit blur, but as you can see here, 87% average precision. And yeah, our model was trained accurately eventually. As you can see below, it's able to recognize the oil tanks in these images. Now, the oil tanks that are in completely white are not floating head oil tanks, and those are not the ones that we want to recognize. The ones we want to recognize are the ones with shadows and are the ones that are marked out by the bounding boxes. Now, next I'll run through with you the notebook of our code. So at the start, we simply installed some dependencies such as milestone2, PyTorch, and we imported various libraries. We imported our data sets, of course, and we configured a model for transfer learning. And then, we trained our data set. So it took quite a while, but we trained it for, as you can see, almost 10,000 iterations. And following that, we performed validation. So we took a sub data set. We divide our data set into a training and validation set. The training set had about more than 9,000 images. We use this to train our model to recognize floating head oil tanks from different angles, from different lighting. And then we use our validation set to see how accurate our model was. And it gave a percentage of 86.2, which is, you can round up to 87%. Yep. But actually the model is more accurate than this. But the oil tanks in our validation set do not take into account the tanks that are cut off halfway at the edge of the image, but our model is able to recognize those. So the system recognizes this an error when in fact it is correct. So average precision should actually be higher, but it's not reflected here. But that's fine because our precision is still quite high. Now, as you can see in this blown up image, you can see the recognition of the oil tanks here, here, and here. And you can even see the image, the oil tank that it recognized cut off halfway, but it's still able to recognize. And you can see the tank in white has not been bounded because it is not a floating head oil tank. And our model is extremely confident 100% for each of these images, giving us pretty good results. Except for the tanks below in brown, which are floating head oil tanks but are harder to interpret because the shadows are not very clear. So we will skip this for now. Now, so far our models is pretty good as it is able to recognize oil tanks. However, to take it one step further to estimate the volume of oil in the tanks itself, as you can see in this image, you can see in the large oil tank in the center, surrounded by the green bounding box, you can see a large shadow cast outside the tank and a relatively small shadow cast inside of the tank. Now, the disparity between the size of these shadows represents how much oil is left in the tank. Because there's a lid floating on the top of the tank, the closer the lid is to the top, the smaller the shadow cast and the more full the tank is. As you can see for the tank above, the shadow cast in the tank is almost the same size of the tank as the shadow cast outside, meaning that this tank is close to empty. So the tank in green is close to full. So comparing the shadow inside the tank and outside the tank is how we are able to estimate the volume inside each tank. Now, estimating the volume based on the shadows is still a work in progress for us, but we are confident that we should be able to get it done by milestone 3. So this is, as you can see, this is the original image. You can see the shadow on the outside. It's a bit blurry because it's been blown up, but you can see that shadow on the outside and the inside, which are relatively the same size, but difficult for a computer to recognize. In the lab color space, the contrast is a bit stronger. You can see the shadow is mostly like a turquoise green, and most of the imperfections inside the shadow are gone. Now when we conduct thresholding of this, which basically takes every pixel that is not above a certain value and converts it to white. So the rest of the values which are part of the shadow are left at blue. So as you can see, it's a lot easier for the computer to recognize now because there are only two values, this shade of blue and white. So it is able to recognize that the blue is the shadow and the white is not the shadow. So it just has to compare, we first have to take out the noise in each of these, in the image, there's all these spots, and basically compare the size of these two crescents. So here it's roughly the same size, so the tank would be perceived to be close to empty. If this shadow was smaller than the other one, then we would perceive the tank to be close to full. Yep. And that is the main gist of our project. Alright, thank you.